In this video, we are going to look at applications of second-order, linear, possibly non-homogeneous differential equations with constant coefficients. And it's surprising how many applications come from this second-order equation. In particular, there's applications such as a vibrating spring, the torsional oscillations of a shaft with a flywheel, the flow of electric current in a simple series circuit, and many other physical problems. They're described by the solution of this initial value problem. In this video and the next, we will be looking at motion of a mass on a spring. And here's the little drawing I have. We have a spring that has its natural length of little l, and then we hang a mass on it, which extends the spring to another capital L units. And the idea for the static problem, which is the easiest problem to start with, is that this system is in equilibrium. In other words, there's no motion. So to be in equilibrium, the two forces acting on the mass are equal. And the two forces that are acting is the gravitational force, or the weight of the mass, which is equal to mass times gravity, which is equal to weight, and it acts downwards. Then there's also the spring force, designated with the capital F and the lower, the subscript S for spring, is equal to minus K. This is a spring constant, which is a constant that is determined by the nature of the spring, times L, which is this additional displacement. And again, if the mass is at equilibrium, or if the system is at equilibrium, the two forces, gravitational and spring force, balance each other, and W is equal to Fs, or W plus Fs is equal to 0. The more complicated problem is the dynamic problem, where the mass can be acted on by an external force. And so U will let U of t be the displacement of the mass from equilibrium at time t. Then from Newton's second law, we have mass times acceleration is equal to the sum of the forces. Where the forces are, and now we're going to have additional forces acting on there, we still have the weight of the mass and it's acting downwards. We still have the spring force, but now the spring force, the minus K, has a length. The length of the spring is not just the L from the mass, but also U, wherever the spring happens to be at the time. And again, the spring force acts to restore the spring to its natural position. We can also consider a damping or resistive force. So we denote that with the capital F and the subscript D, D for damping, and that's equal to minus gamma U prime of t. Basically, the damping force acts in the direction opposite motion of the mass, which is why there's this negative, and proportional to the speed of the mass. Proportional, that's why we have this, this constant coefficient in front of the speed. So that's the damping or resistive force. And then we can have an applied external force, F, which is positive when directed downward, often periodic. And then since mg minus KL equals 0, the equation becomes, and I've also written it up here, mu double prime plus gamma u prime plus ku is equal to the external force. We are going to look at, in particular, damped free vibrations. In other words, we're going to have damped, or this dampening resistive force, free meaning there's going to be no external force. In the next video, we'll add external forces. And our equation becomes mu double prime plus gamma u prime plus ku equals 0. If you look at this equation, you see the form is a second order linear differential equation with constant coefficients. And we know how to solve those. We take the characteristic equation and we solve for the roots. And if you remember, there are three possibilities for the roots. One, you can have two distinct real roots, and that's when this over here, what's under the square root, is positive or greater than 0. And in which case, you will have an overdamped situation where you have this exponential decay of the position of the spring. Or if R, the other possibility is this, what's under the square root can equal to 0. That's when you have the case of a critically damped exponential. And then if you recall, this is what the solution would look like. And a critically damped, again, you still have the e to the minus, and then you have these exponential decays, but you also have this t here. So initially, the t contributes, which gives us a little bit of a positive bump, but eventually the decay starts to take over as t gets large and you decay down. The last possibility for underneath the square root is if you have an imaginary root, and that's over here in the small damping. So when this is less than 0, then we have an imaginary solution, and we'd like to look at it in this form here, which we'll talk about more. But essentially what you have is you have a oscillating or a cosine kind of wave, but it's enveloped by this decaying function. So this decaying function kind of provides an envelope, so you can see that the oscillations become smaller and smaller until they eventually peter out. Your book calls this small damping, but everyone else in my family who's either a physics major or electrical engineer or some combination thereof assure me that I should really be saying underdamped. But this is what your book says, so I'm going to use the term small damping. With that out of the way, we are ready to get into details. We are looking at motion of mass on a spring, so we're going to consider a mass m hanging at rest at the end of a vertical spring of original length little l. The mass causes an elongation capital L of the spring in the downward positive direction, so we hang the mass and we have this extra elongation capital L of the spring in the downward direction. In the static situation where the mass is hanging and there's no motion, the forces acting on the mass, where the mass is attached to the spring, are first the gravitational force. That's the weight of the mass is equal to mg, and it acts downwards, pulling it downwards. By the way, downwards is the positive direction. The spring force, designated with the capital F and the subscript s for spring, is equal to minus KL, that acts upwards, trying to restore the spring to its unhindered state. So if the elongation capital L of the spring is small, the spring force is nearly proportional to L, and this relation is known as Hooke's law, and that's what is written here. So the spring force is proportional to L, and this minus K, or the K by itself is known as the spring constant, and its units is force per unit length. Since the mass is at equilibrium, in other words, it's not moving, the two forces, the gravitational and spring force, balance each other. In other words, W is equal to the spring force. Or you could also say W plus the spring force is equal to 0. And then rewriting W as mg, the spring force is minus KL, and we have mg minus KL is equal to 0. So for a given weight, once you know the weight, you can measure L, and then you can use this equation over here, mg minus KL, to determine K. And that's mostly what we're going to be using the static situation for, is to calculate the value for K. We will continue to the dynamic problem. So the mass can be acted on by an external force, F of t. Let u of t be the displacement of the mass from equilibrium at time t. Through Newton's law, we have F, that's our forces, is equal to mass times acceleration. And the forces are 1, the weight of the mass acting downwards, the spring force, and now we have this additional displacement of u. So we have minus k times L plus u, and it always acts to restore the spring to its natural position. There's some other notes here, which I'm going to skip, but essentially it just confirms that whether the spring is extended or compressed, that this is the equation we want. Then we can have a damping or resistive force, and we'll designate that with capital F, subscript D, D for damping, is equal to minus gamma u prime of t. And it acts in the direction opposite the direction of motion, hence the minus sign of mass, and it's proportional to the speed of mass. Hence, we multiply the speed of the mass times a constant, gamma. So this force, this damping force, may arise from several sources, such as resistance from air or other media which the mass moves, or it could be friction. Remember in physics in freshman year how we kept saying we were going to ignore air resistance or we were going to ignore friction? Now we can add it back in, now that we know differential equations. Anyway, the last force is the applied external force, F of t, directed downward if F is positive, or it can be directed upward and F is negative. And often the external force is periodic. In this video, we're going to skip F, but in the next video, we'll look at having F. Anyway, Newton's law then becomes, again, we have the forces equals mass times acceleration. So we have the forces of weight, the forces of the spring force, the damping force, and the external force. So plugging in our other parameters, we have weight is equal to mg. Our spring force is minus k times L times the displacement. And our damping force is minus gamma times the velocity plus the external force. Since mg minus kl equals 0, that will kind of cancel this and this term out. Our equation becomes u double prime, that's this part over here. Moving this over, we get plus gamma u prime of t, and then we have this k times u of t. Moving it over to this side of the equation, we get plus k u of t equals our external forces. And then we can also have initial values. Our first example is we have a mass weighing 4 pounds which stretches a spring 2 inches. Suppose the mass is given an additional 6-inch displacement in the positive direction and then released. The mass is in a medium that exerts a viscous resistance of 6 pounds when the mass has a velocity of 3 feet per second. Formulate the initial value problem that governs the motion of the mass. First, I wrote down my differential equation from Newton's law. So my m double prime is equal to my forces, which is my weight, plus my spring force, my damping force, and any external force. The weight is mg, my spring force is L, or minus k, the spring constant, times the displacement, in this case, which is our displacement of the mass, plus displacement, my additional 6-inch displacement, minus my damping, plus my exterior force. So looking again at this picture, it says that the mass displaces the spring 2 inches. So that's my capital L. And I'm going to convert everything to feet. So that's 1/6 of a foot. And then we're given an additional 6-inch displacement from this diagram. That means that's U. Is going to be our 6-inch displacement, which is half a foot. Our damping coefficient. Remember, the damping is a number of force, and it's in the opposite direction of motion, so it has to do with the velocity. So here we have 6 pounds when velocity is 3 feet per second. So that's 6 pounds. That's not 61 BS. That's 6, and that's an L BS. So 6 pounds per 3 feet per second. So that's equal to 2. And then last, our weight is equal to mg, so that's 4 pounds, which means our mass is equal to 1/8. Since the mass, when it's at equilibrium, before we give it that extra 6-inch displacement, the two forces balance each other out, the two forces being the weight and the spring force. So the weight is 4 pounds, the spring force is k times the displacement, and that's the displacement that the mass gives it, which is 2 inches or 1/6 of a foot. So k is equal to 24 pounds per feet. Now I'm ready to plug in to my equation. My mass, I said, was 1/8 u double prime plus lambda is equal to 2 times u prime plus k, our spring force, is 24 times u, and our homogeneous equation equals 0. So our initial conditions, initially, our displacement is at 1/2, that's given to us. We were displacing an initial 6 inches. And then our initial velocity is equal to 0. So solving for this, this is our equation, multiplying everything by 8. I get u double prime plus 16u prime plus 192u equals 0, with u of 0 equals to 1/2 and u prime of 0 equals to 0. And this equation here that I used came from the fact that I knew that mass gram minus KL is equal to 0. So this was the equation I used here. If I had used this full equation with mass times gravity, sorry, not mass gram, mass times gravity, and then K times the full displacement, I would have come up with the same equation. So in this case, either equation would have worked, this one here or this one that simplifies where mg minus kl equals 0. Now we're going to focus where we have no external forces. So we're going to add the damping coefficient and we're going to have f of t equals 0. So now we have this second order linear, homogeneous because f of t is equal to 0, differential equation with constant coefficients. Remember mass, gamma, and k, they're all constants. So when we solve our differential equation, remember when we solved second order linear homogeneous differential equations with constant coefficients, we would look at the characteristic equation. So the characteristic equation for this differential equation is mr squared plus gamma r plus k equals 0. And then this we would use our binomial theorem to solve for r. There were 3 possibilities for roots of this characteristic equation. The first one was R1 and R2 are real and not equal. They were 2 distinct roots. Then the general solution would be y equals c1 e to the r1t plus c2 e to the r2t. So that was a very straightforward one. The second one is if r1 and r2 were complex conjugates, and that occurs when this part of the square root is negative. And then our general solution was c1 e to the lambda t cosine mu of t plus c2 e to the lambda t sine of mu of t. And how did we get that? We looked at our complex coefficient if r was equal to, say, lambda plus or minus I mu, so lambda being a constant and mu being a constant. Then we used this definition from Euler that e to the lambda plus I mu of t would be equal to e to the lambda t, so taking this portion, e to the lambda t, and then this e to the I mu would equal to cosine mu of t plus I sine mu of t. So our entire e to the lambda plus I mu t would equal to e to the lambda t cosine mu t plus I e to the lambda t sine mu of t. There was one other thing we did, and that we had this theorem that said if you had the second order linear equation and you had a complex valued solution, in other words, a real part plus I times another real part. So here we have a real part of a solution plus I times another real part of the solution. Then we also had this theorem that said the real part u, over here, and in the imaginary part, the v part, which is real without the I, right, the v without the I, would also be a solution. So what we did is we would drop the I and we would take the solution to be c1 e to the lambda t cosine mu t plus c2 e to the lambda t sine of mu t. So we dropped the I here because of this theorem. The last case for this characteristic equation for the roots is if r1 is equal to r2. In other words, this part of the square root was equal to 0. Then what we found is first we had our first solution would be e to the rt, and then we found if we just multiplied by t, we could get a second solution. So this was our solution when we had equal roots. For our first look at these undamped free vibrations, we're going to try to simplify as much as possible. We're going to first set the external force equal to 0 and also the damping equal to 0. That simplifies our equation to mu double prime, this would be 0, plus ku is equal to 0. So this is what we're left with our second order differential equation here. We can look at the characteristic equation and we see that we're going to get complex roots. Complex roots means we're going to have sines and cosines. In particular, our solution is going to be of the form a cosine omega t plus b sine omega t, where omega is equal to the square root of k over m, or omega squared is equal to k over m. And how did I get this? Well, remember, we use these two things when we are solving for roots, that are complex roots. One, we use Euler's formula, and we use the fact that once we have a solution with complex values, we can just take the real parts, u and v, as solutions. So if I look at e to the, and using my r equals I to the square root of km, so I have e to the I square root of km times t. using this formula here, so I have my mu is equal to square root of km. I don't have any lambda t. So that's going to be equal to cosine a square root of kmt plus I sine a square root of kmt. And then I can replace my square root of km with omega if omega squared is equal to k over m. And then the last thing I do is I can just take this part, the real part of I sine km, and that can be another solution. So here is my general solution. There is one more trick we want, and that is here we have our solution for u, but we want the form to look like this. We want an r cosine omega naught t minus delta. Why do we want this form? Well, this is kind of easier to see what's going on. It's one simple sine wave instead of a combination of two. We have our phase, what we consider our phase here, and r is our amplitude. It makes it easier to kind of read off what's going on. So how do we get this in this form? Well, we're going to consider this equation here, which is r cosine delta cosine omega naught t, r sine delta sine omega naught t. And what we'll note is we can use this trig identity here, where if we have cosine A cosine B, which is what we have here, and sine A and sine B, that will be equal to cosine A minus B. So that's exactly what we want. We have cosine omega naught minus delta. And then we have the r in front where, so now we just need to relate it back over here. Well, if I compare this equation here to what we have for u, if I let A equal to r cosine delta and B equal to r sine delta, then u is in exactly this form. So we have r is equal to, just from these two equations, square root of a squared plus b squared, and tangent of r delta is equal to b over a. I have summarized what we talked about here. We had an undamped free vibration. So again, undamped meaning our damping is equal to 0, free meaning our external force is equal to 0. So we came down to mu double prime plus ku equals 0. We saw the general solution would be equal to u is equal to a cosine omega t plus b sine omega t, where omega naught squared is equal to k over m. But we wanted to put things into this form of r cosine omega naught t minus delta, and we did that by letting a equal r cosine delta, b equal r sine delta. And we like this form because it allows us to read off an amplitude, a frequency, and a phase fairly quickly, as opposed to trying to figure out what's going on with this the superposition of two waves. Looking at this equation, we see the graph is a displaced cosine wave that describes a periodic or simple harmonic motion of mass. And here we have our equation for the period is equal to 2 pi over omega naught, which is equal to 2 pi times m over k to the 1/2. The circular frequency, omega naught, which is equal to square root of k over m, is measured in radians per time, is called the natural frequency of the vibration. The maximum displacement r of the mass from equilibrium is the amplitude of motion. And the dimensionless parameter delta is called the phase or phase angle, and it measures the displacement of the wave from its normal position corresponding to delta equals 0. So it's kind of just this shift over from 0. A couple of other notes. The motion has a constant amplitude that does not diminish with time, and this reflects the absence of damping. Further, for a given mass m and a spring constant k, the system always vibrates at the same frequency omega naught, regardless of the initial conditions. Although the initial conditions do help determine the amplitude, the period t, which we have the equations for here, which is equal to 2 pi over omega naught, or 2 pi times m over k to the 1/2, increases as the mass increases. We can see that here. So larger masses vibrate more slowly. T decreases as the spring constant increases, and we can see that here, which means the stiffer spring causes the system to vibrate more rapidly. And here's an example. Suppose a mass weighing 10 pounds stretches a spring 2 inches. If the mass is displaced by an additional 2 inches, then set in motion with an upward initial velocity of 1 foot per second, determine the position of the mass at any time later. Also determine the period, amplitude, and phase of the motion. So I've written some of this stuff down. Our weight is equal to 10 pounds. The mass displaces the spring an additional 2 inches, which is 1/6 of a foot. My u naught of 0, the position at time 0, is equal to the 1/6 of a foot, and my u prime at 0, at time 0, we give it an initial velocity of 1 foot per second upwards, so that's minus 1 foot per second. So we can find k, again, by using mg equals kl. So our weight is equal to 10, is equal to k times L. So our L is, 1/6 of a foot. So K is equal to 60 pounds per feet. And mass, by the way, if you need it, is just going to be W over G, which is 10 over 32 feet per second. I'm not sure I really like using inches and pounds instead of the metric system, but I'm certainly not going to convert these problems from your book. So here we are with pounds and feet per second. Here I copied my equation from over, where did I copy it? From over here. Mu double prime is equal to mg minus kl plus ut minus our damping times the derivative of the speed plus f of t. So I wrote that down here. And again, we said that looking here, there's no damping and there's no external force. So we have m, which we calculated here, 10 over 32, u double prime is equal to our weight, which is 10, minus k, which is 60, times L, which is 1/6, plus u of t. Doing the arithmetic, we get then 10 over 32 u double prime plus 60 u is equal to 0. I have a quick note. I could have just used, instead of this equation from up here with all of this other stuff, I could have just gone for this equation, knowing that this is undamped free vibrations. I could have just done this and gotten here quicker. Well, I can now multiply everything by 32 over 10, and I get u double prime plus 192u is equal to 0. So this is our differential equation. I summarized everything here so I could have a little more space. Again, here I have the calculations for k, the calculations for mass. My second order differential equation ended up being u double prime plus 192u equals 0. I also calculated what w naught, the frequency, would be equal to. Since we did some of the work in general, I went ahead and just used this information up here. So my u of t, so my position at time t, is going to equal to a cosine, and then I plugged in my w naught, 8 square root of 3t, plus b sine of w naught times t. I use my initial conditions that u naught is equal to 2 over 12 feet, and that's equal to, and then if I plug in 0 here, this goes to 0, this goes to 1, so it's equal to a, so a is equal to 1/6. I calculate u prime, and then I plug in 0, so now what goes to 0? The sine goes to 0, this must be cosine, so I get 8/3 times b. And that will give me b is equal to minus 1 over 8/3. So here is my final solution for u of t. It's equal to 1/6 cosine of 8 square root of 3t minus 1 over 8 square root of 3 sine of 8 square root of 3t. The next thing that it asked for was period, amplitude, and phase of motion. So I plugged in then for my period. T is equal to 2 pi over omega naught, which is 8 square root of 3. So that's approximately 0.453. I also needed my amplitude. R squared is equal to a squared plus b squared. So that would be 1/6 squared plus 1 over 8 square root of 3 squared, which would give me 192. So my R is approximately 0.182. My tangent of delta is equal to b over a, so that's approximately equal to negative 0.40864 radians. Last, I really should have put this in this other form of r cosine omega t minus delta, but I didn't. I'm just going to leave it in this form. Next, we're going to put in damping. So we're going to look at damped free vibrations. So we're going to focus on the damping coefficient. We're going to set its free vibrations because we have no external force. So capital F of t is still equal to 0. Again, we have our second order differential equation, but now we have damping in here. So we have our mu double prime plus gamma u prime plus ku equals 0. And our characteristic equation looks like mr squared plus gamma r plus k equals 0. And then we solve for our roots using the binomial equation. And we get r is equal to minus gamma plus or minus square root of gamma squared minus 4km all over 2m. We talked about this a couple of slides back. So there are three possibilities for solutions to this characteristic equation, depending on what happens to what's under the square root. So if gamma squared minus 4km, it could be either greater than 0, equal to 0, or less than 0. If it's greater than 0, we're going to have two real solutions. So our u, or our solution to the differential equation, will have the form of a e to the r1 of t plus b e to the r2 of t. And we will also note, since m, omega, and k are all positive, that means this root is going to be negative. So r1 and r2 are negative. So these are exponential decays. The other possibility for what's going on behind the square root is that it's equal to 0, in which case we have one single root, or two roots that are equal, and we learned how to solve that for second order linear differential equations homogeneous with constant coefficients, which would be equal to a e to the first root, which will be minus gamma t over 2m, plus, and the same exponent, but now we put a t in front of it. So if we have equal roots, we're going to have a e to the minus lambda gamma t over 2m plus b t e to the minus gamma t over 2m. And again, because m, gamma, and k are all positive, that means our roots over here, these are negative. So we have an exponential decay here, and we have an exponential decay paired with some linear increase. Last, if underneath the square root we have something negative, we're going to have complex solutions or complex exponents. And then if r is complex, what we found is that in which we discussed this in the previous slide, we'll have e to the minus gamma t over 2m times a cosine mu of t plus b sine mu of t, where mu is equal to 1 over 2m square root of 4km minus gamma squared. As I had mentioned before, since m, gamma, and k are all greater than 0, that means our roots in these exponents are all negative. That means we're going to have these exponential decays. So as t approaches infinity, our position of the spring at time t is going to approach 0. In other words, because of the damping will dissipate the energy, and motion will die out. And this is regardless of the values of A and B, which is basically the same thing as saying regardless of the initial conditions. The damping will always cause the motion to die out. This is probably a better summary of what's going on here. So we have our second order differential equation, our characteristic equation, our root, and then the three different cases for our roots, and then the conclusion here as t approaches infinity, our motion will go to 0. Regardless of initial condition, energy is going to be dissipated, motion dies out. And next we're going to look at these three examples. And now we're going to take a look at these three conditions. Here we have gamma squared minus 4km is greater than 0. That again gives us this oscillating our sines and cosine kind of equation. This is called small damping or underdamped. When underneath the square root we have something equal to 0, that's called critically damped. And this is the form of our equation. Again, we have our exponential decay, but we do have this t, which early on gives us a little bit of an increase. And then last we have overdamped, when what's underneath the square root is greater than 0, and we can have our two roots, and then we have straightforward a decay. And one of the things that's really important to notice is it's not the magnitude of gamma alone that determines whether damping is large or small, right? So we have three different types of dampings: the small or underdamped, critically damped, and overdamped. But we're not just looking at gamma to determine it. We have to compare gamma to 4 km, and that's what determines kind of the behavior of our damping function. We will start with small damping, and that's when what's underneath the square root, this gamma squared minus 4 km, is less than 0. So we have imaginary roots, which gives us this cosine sine kind of solution. And we also have the e to the minus gamma t over 2m, multiplying our cosine sine. To analyze this, we want to put this in the form of r cosine omega t minus delta, because that allows us to read off an amplitude, a frequency, and a phase. We did that for another previous example, and essentially what we did is we looked at this equation here, r cosine delta cosine omega t plus r sine delta sine of omega t. You know, when you use this trig identity, it simplifies down to r cosine omega t minus delta, which is exactly what we want. When we compare that with what we have, we see we can get this by setting a equal to r cosine delta and b equal to r sine delta. Then we have r is equal to a squared plus b squared, and tangent d is equal to b over a. So we have this form of the equation, okay, because right now we're not solving a particular one, but in general, we're going to get it into this form here, where we have our r and our cosine mu of t minus delta, and then we still need to multiply by this part here, the e to the minus gamma t over 2m. We can look at this now, and it's actually not exactly periodic because it is decaying, but we call r sort of our amplitude factor because it does give us like a maximum height in kind of a local area. We call d our phase. We call mu our quasi-frequency. Again, it's not a frequency because we don't have true periodic motion, but you know, mu is sort of our quasi-frequency. And our gamma now, that came from damping, gives us our envelope, because our gamma, if you look at where does it appear in this equation, it's here in the decay part, the exponential decay. So if we just look at our r e to the minus gamma t over 2m, we get this envelope of decay, and then from the negative part, we get this envelope, well, it kind of comes up. So what this envelope does is this is what contains our oscillations. And as this decay goes down, our oscillations kind of get smaller and smaller until they eventually die out. So here again, our displacement will lie between plus and minus r e to the minus gamma t over 2m, this envelope here. Again, it's this gamma, again, our damping that is kind of decreasing or making our oscillations peter out. Hence a cosine wave whose amplitude decreases as t increases. So a decreases by, in particular, it decreases by e to the minus gamma t over 2m. And r is the amplitude factor. It depends on m, gamma, k, and the initial conditions. And you can see that here, right? R depends on the initial conditions, and then also on the delta, so it depends on m, gamma, and k as well. I kept my summary of small damping over here, right? Our initial solution, and then later we put it into this form, our cosine omega t minus delta times e to the minus gamma t over 2m. And I also wanted to say, or I kind of mentioned this already, but I wanted to note that although the motion's not periodic, the parameter mu over here determines the frequency with which the mass oscillates back and forth. So mu is called the quasi-frequency. Comparing mu with the undamped motion, so we can look at mu compared with the frequency. So I have the formula for mu here, the formula for frequency. What we see is that's equal to 1 minus gamma squared over 8 km. In other words, the ratio here is a little less than 1. So we expect mu to be a little smaller than the true frequency. And this last approximation is valid when damping is small, thus we call it small damping as opposed to underdamping. By analogy, the quantity, we're going to call this capital TD, that's the period with damping, is equal to 2 pi over mu, and it's called the quasi-period of the motion. It's the time between successive maximum or successive minimum. And the relation between TD and T is given here by the ratio, and what we can see is it's equal to 1 plus gamma squared over 8 km. Thus, small damping increases the quasi-period. So that's all I'm going to say for now about small damping. These next two are even easier. The overdamp function, again, that's when what's under the square root is greater than 0. So we do have two roots, R1 and R2, two real roots. Since R1 and R2 are both negative, the graph is an exponential decay to equilibrium. It's straightforward a decay. There's no oscillations, right? There's no sines, cosines. There's nothing else. It's just a decay, which is why it's fairly easy. And in the case of critically damped and overdamped, the mass may pass through its equilibrium position at most once and then creep back to equilibrium. The mass does not oscillate about the equilibrium, and it does as it does for small damping. And that's all we're going to say for now for overdamped. And we can look at critically damped. Again, that's when what's under the square root is equal to 0. So the gamma squared minus 4 km is equal to 0. So we have equal roots. And what we do, the way we approach that, is we have e to the first root minus gamma t over 2m plus bt times the same e to the minus gamma t over 2m. And here r is less than 0. So there's going to be an exponential decay. But the t in this right here, this t right here, so the t in the e to the rt term, this one, will increase u for a little while, which is why we get this little increase. When t is small, the t in t e to the rt will cause u to increase, but as t increases, the e to the rt, this part, the decay part, will dominate, and then we'll start to get a decay. And again, the same note, as in the case of critically damped and overdamped, the mass may pass through its equilibrium position once, and that's what I have here. It passes through equilibrium at most once, and it overshoots a little bit, and then it comes back down, it decays back down. The mass does not oscillate. There's no sine and cosine here. It's just, a little bit of increase, linear increase here, along with the two decay functions. So it does not oscillate about the equilibrium as it does for small damping. And so that's it for the 3. And again, remember, it's not the magnitude of gamma alone that determines what happens here. You have to look at gamma compared to the 4 km. And I have these tiny little graphs that I cut and pasted over here so I could include them in my summary. Here's my small damping, my critically damped, and my overdamped. And here is my summary up here. Again, my differential equation, my characteristic equation, my R, the quasi-frequency, the quasi-period, the small damping solution, the critically damped solution, and the overdamped solution. And now we're ready for an example. The motion of a spring mass system is governed by u double prime plus 1/8 u plus u equals 0, where u is measured in feet and t in seconds. U of 0 is equal to 2, u prime of 0 is equal to 0. Find the quasi-frequency and the quasi-period, as well as the time at which the mass passes through its equilibrium position. Also find T1 such that the absolute value of u of t is less than 0.01 for all t greater than T1. Our characteristic equation is going to be r squared plus 1/8 r plus 1 equals 0. So we can solve for r, and we get minus 1/16 plus or minus I square root of 255/16. So this I means this is a small damping problem, and our solution is going to have the e to the minus 1/16 times t, or e to the minus t over 16, plus our sine and cosine of a cosine square root of 255 over 16 times t, plus b sine square root of 255 over 16 times t. We can use our initial conditions. U of 0 is equal to, when we plug in 0 here, this becomes 1, this becomes 0, so it's equal to A, which is equal to, where's our initial condition? 2. U prime, so here I did the derivative of u. It ended up being quite long because of so many functions of t. And when we plug in 0 into the derivative, which I have calculated here, plugging in 0, we get that b is equal to 2 over square root of 255. So our final solution, our general solution to the homogeneous equation is u of t is equal to e to the minus t to the 16th, 2 cosine square root of 255 over 16t plus 2 over square root of 255 sine of square root of 255 over 16t. I moved my solution here, but I want my solution to be in this form, my r cosine omega t minus delta. So I let a equals r cosine of delta and b equal r sine of delta. And then r is going to equal to a squared plus b squared. That will be 4 plus 4 over 255, which is equal to, conveniently, 32. Tangent of delta is equal to b over a. So b over a will give me 1 over square root of 255. So delta is approximately 0.06254, which gives us u of t is equal to e to the minus t over 16, 32 over square root of 255 cosine a square root of 255 over 16t minus our delta. I'm sorry, I keep having to rearrange things to give myself more space, but these problems are so long. So once I have my equation for u of t, I can read off my omega, which is square root of 255 over 16. I can then calculate my quasi-period, which is equal to 2 pi times 16 over 255. And last, to see where this passes through equilibrium, where we are at 0. So here, the only way we can get this to 0, 32 isn't going to be 0. This is never going to be 0. So we need the cosine of square root of 255 over 16t minus delta to equal to 0. So I plug in my delta here, and I solve, and t is going to be 1.6375. We've gone through this motion of mass on a spring, in particular the dynamic problem, which gave us these 3 cases of small damping, critically damped, and over-damped. But now we want to look maybe at one more application. And our last example is electric circuits. So here is, I guess it's a circuit. We have a resistance, a capacitor, inductance, I don't know, a switch, and an impressed voltage. I'm sorry, I'm not a physicist, although I did take E&M like over a decade ago. Anyway, and then we have current going around. So our functions of time include current, and it's measured in amperes. It's a function of time. We have the impressed voltage E, which is measured in volts, and it's also a function of time. We have total charge Q, which is measured in coulombs on the capacitor at time t. And we also have this formula that current is equal to dq dt. Our known positive constants are resistance R, which is measured in ohms, and we should also know that the voltage drop across the resistor is equal to R times I being current. We have capacitance C, which is measured in, what are those, farads? And the voltage drop across a capacitor is Q over C. Then we have inductance, L, which is measured in henries, and the voltage drop across the inductor is L di dt. So this is what will give us an equation now that we know these constants and our functions. The flow of current in the circuit is governed by Kirchhoff's second law, that in a closed circuit, the impressed voltage, that's what, E? Yeah, the impressed voltage is equal to the sum of the voltage drops, which I have mentioned here, in the rest of the circuits. So Kirchhoff's law says that E of t is equal to the voltage drops. So we have L di dt, we have Ri, and 1 over C times Q. I also have this here in case you're interested. I don't know if it's helpful or not. I didn't use it. Anyway, Kirchhoff's law, if we set I is equal to dq dt, and that was a formula that was given to us, I've rewritten Kirchhoff's law here, L di dt plus Ri plus 1 over CQ is equal to, now if I substitute I is equal to dq dt. So this is L, and I is dq dt. So I put in dq dt here for I, and I have d dq dt dt plus r, and then I is equal to dq dt plus 1 over c, and then we have q. So what that gives us is L q double prime plus r q prime plus 1 over cq is equal to et. So here we have our second order linear, it's non-homogeneous differential equations. L, R, and C are all constants, so it's with constant coefficients. So this is exactly what we have been looking at. Thus, to know the charge at any time t, it's sufficient to know the charge on the capacitor and the current in the circuit at some time, initial time t naught. I guess, yeah, the capacitor and the current, right? Because C and R are just constants. So from Kirchhoff's law, we can obtain a differential equation for the current by differentiating with respect to t. So here we differentiate with respect to t, ddt of LQ double prime plus RQ prime plus 1 over CQ. That gives us ddt LQ triple prime plus RQ double prime plus 1 over CQ prime is equal to E prime of t. And again now, using I is equal to Q dt, that gives us Li double prime plus Ri prime plus ICI. So now we have a second order differential equation in terms of the current I is equal to E prime of t, and then we can have some initial conditions. So I have rewritten that last differential equation for I right here, so that then I can move this equation. I'm just going to move Kirchhoff's law equation over here, which is Li prime plus Ri plus 1 over CQ is equal to ET. And if I solve this equation for I prime, I get I prime is equal to ET minus Ri minus Q over C, all divided by L, which means that I naught prime is equal to ET naught minus Ri naught minus Q naught C over L. So I naught prime is determined by the initial charge and the current, which are physically measurable quantities. A series circuit has a capacitor of 10 to the minus 5 farads, a resistor of 3 times 10 to the second ohms, and an inductor of 0.2 henries. The initial charge on the capacitor is 10 to the minus 6 coulombs, and there is no initial current. Find the charge Q on the capacitor at any time t. I started by just rewriting everything. C is equal to 10 to the minus 5F, R is equal to 3 times 10 to the 2 ohms, L is equal to 0.2 H, Q naught, right? That's the initial charge, is equal to 10 to the minus 6 C, and there's no initial current, so I T naught is equal to Q prime naught. I have to remember that, right, from this equation here, and that is equal to 0 amperes. So the impressed voltage E is equal to 0 by Kirchhoff's law is equal to LQ prime RQ prime plus 1 over CQ. So we have L, which is 0.2 Q prime, plus R, where's R, is 3 times 10 to the 2 Q prime plus 1 over C, which, where's C? C, which is 10 to the 5th Q, is equal to 0. Ooh, and now we have a second order differential equation. And we can solve that because we can have our characteristic equation, which is 0.2 r squared plus 300 r plus 10 to the 5th equals 0. So we can solve this for r, and we get r1 is equal to 500, minus 500, and r2 is equal to minus 1,000. So Q of t is equal to AE to the minus 500t plus BE to the minus 1,000t. So this is a straightforward overdamped solution. We can solve for A and B using the initial conditions, which I have done here. So my final solution is QT is equal to 2 times 10 to the minus 6 e to the minus 500t minus 10 to the minus 6 e to the minus 1,000t. So we did a lot in this video. We looked at applications of the second order linear, possibly non-homogeneous differential equations with constant coefficients. In particular, we looked at motion of a mass on a spring. We looked at the static problem. when the only two forces were the gravitational force and the force of the spring that would work to restore the spring to its natural position. And since it's at equilibrium, we assume the two forces were at balance. In other words, the gravitational force is equal to the spring force, or in other words, W plus Fs is equal to 0. Next, we looked at the dynamic problem. We let U of t be the displacement of the mass from equilibrium, and then we said that the forces using Newton's second law would equal to the mass times acceleration. And the forces included, again, the weight of the mass acting downwards, the spring force. Now it was equal to minus k, the spring constant, times the displacement, the total displacement L plus U. We also looked at a damping or resistive force, F of d, which is directly proportional to the speed of the mass, u prime of t, but it's in the opposite direction, so it was negative. We looked at and applied, we skipped the applied external force F. We did solve for it in general, but in our examples in this video, we let F be negative. External forces will come in the next video. When we looked at these motion of a mass, when we added back in damping, but still we had no external forces, we had this second order differential equation, mu double prime plus gamma u prime plus ku is equal to 0. We looked at the characteristic equation and we said there were three possibilities for roots. First, it could be that what's inside the square root was less than 0, in which case we would have complex roots, and we would have a solution of this form, e to the minus gamma t over 2m, and then a cosine mu of t plus b sine of mu of t. We worked using a trigonometric identity to get this into the form of u equals r e to the minus gamma t over 2m cosine mu t minus delta. And what we saw is this form tells us that there are oscillations in our solution, but there's an eventual decay, and so our e to the minus gamma t over 2m gave us this envelope here, or also times r, gave us this envelope, and within that was the cosine function that then gets dampened until it eventually goes to 0. A critically damped function is what we get when what's inside the square root is equal to 0. Our solution will look like a e to the minus gamma t over 2m plus bt e to the minus gamma over 2m. And what that tells us is we do have this decay, but for a little while, this t will act to kind of increase. As t increases, it'll increase our function, but eventually the decay will take over for larger values of t, and we'll get this eventual decay. So that's what our critically damped solutions look like. And then our overdamped solution is when what's under the square root is greater than 0. So we have two roots. And so our solutions look like u is equal to a r1 to the t plus b r2 to the t. So this is straightforward a decay. So here we have our overdamped solution, which is just an exponential decay. So those were our three types of kind of dynamic problems when we had damping. We did also look at a more straightforward solution, which I didn't summarize here, when we had no damping and no external force. Our last example was this electric circuit. We found that we can reduce it to a second order linear differential equation with constant coefficients. So we were able to solve those problems as well. So that's it for this video. Thank you for watching.